Hello, my name is Vinicius Ponte Machado, and I will present a paper called "An Hybrid Descriptor to Improve Kidney Pathologies Classification." We from Federal University of Piauí from Brazil. We start with the problem definition. In the United States of America, chronic renal failure affects between 11 and 20 million individuals, while in Brazil there are maybe about 1 to 4 million people with this disease. The kidney pathologist treatment is expensive and can affect the work capacity even in young people, which ends up causing an economic impact to the social security system. So our motivation is assist the pathologist in defining assertive diagnosis based on clinical data and patient's renal biopsy image using machine learning. Using as input the join of clinical data and kidney biopsy image descriptor to each previously known diagnosis. So, our objectives are verify if the clinical attributes alone are capable of returning good results. Use several descriptors to classify images of renal pathologies together with a clinical data. Check if the combination of one or more descriptors with the clinical data is feasible. Verify which tested learning algorithm best applied to the task of classifying renal pathologies. In this work, we tested 4 algorithms, machine learning algorithms. Decision tree using entropy in these parameters, random forest with 100 tree using Gini coefficient, SVM linear kernel with a maximum of 1,000 iterations, MLP 100 hidden layers with 100 neurons each, ReLU activation function. For data preparation, we use the feature selector that enhances the recognition rate with the last number of elements and that generates a set of similar features for the object with similar aspects. We also use resampling, way to get around the problem of an unbalanced dataset, generate new samples in order to make it balanced. Now, we're talking about clinical database. One of our main concern is quantity, both with regard to few examples of some classes and small amount of samples. Here, in the right picture, we can see how many features are needed to describe the complete set of 100 samples from clinical dataset. We can view that only about 20 features here are required to describe the clinical dataset. The image dataset has 71 images whose height and width dimensions are varied. Therefore, not all clinical data have a corresponding image. In the left figure, we present renal biopsy image samples from the image dataset, demonstrating the degree of variety of the available images. There are 28 diagnoses associated with the clinical dataset. To solve the dataset imbalance problem, we apply resampling. After the procedure, all classes contain 7 examples each. This figure summarizes the steps taken in this work. The first step in the data classification was the implementation of image preprocess, in which images are transformed to gray levels, resized to 512 by 512 pixels, normalized, and, finally, perform an equalization in your histogram to eliminate noise. The descriptors grouped in the region highlighted in red figure are descriptors that transform an image into its frequency domain. The yellow region groups the descriptors that extract texture information. Finally, blue region highlights the global descriptor HOG. This descriptor analyzes the image as a whole, analyzes the intensity of the image gradient in various directions. Next, we concatenate the CD, the descriptor images, descriptor, and select features through the mutual information select. After this step, we perform the resampling produced to balance amount of example per class by duplicating examples of minority classes. Finally, the next step in the process was classification. The tested learning methods were decision tree, SVM, random forest, and multi-layer perceptron. So, we're talking about the results and make some discussion about this. In our test, we use two types of database. Pure set contain only clinical attributes or only image descriptor, and a hybrid set that has both clinical attributes and image attributes. Tests of the second type varied by the number of descriptors. To analyze the classification results, we build the confusion matrix. Then, from the elements of this matrix, we calculate the accuracy, precision, recall, and F-score. We also calculate kappa index, which is recommended as an appropriate accuracy measure to represent the confusion matrix adequately. Each descriptor studied was combined one by one with clinical data to obtain those that return the best kappa coefficient. The test case was defined as follows. 1. Clinical data only one image descriptor, no clinical data, and clinical data plus image descriptor, ranging from 1 to 4 descriptor. The results present in table show all classifiers are archived by the best results with the hybrid features vector as input. We also observe that random forest classifier using clinical data plus hog descriptor archive the best performance than the other combinations. In the radar figure presents a comparison of the classifier best performance in these scenarios. On this slide, we can see the best results obtained comparing pure classifier and the best hybrid results. The figures represent the comparison of the classifier's best performance in three scenarios: using only clinical data features, using only image descriptor, and the concatenation among clinical data and image descriptor. The clinical data and image descriptor archive an accuracy rates between 86.74% and 94.99%. This descriptor, archived by the kappa index, was rated as excellent. Moreover, the result was improved by concatenating them, reaching an accuracy of 98.46% and kappa of 98.42%. The figure here shows some items of the random forest classifier confusion matrix using clinical data plus hog descriptor. We observe in this figure that two errors, here and here, made by the classifier were for disease that had 25 or more clinical characteristics in common. These images are quite similar, which may have induced the classifier to make these mistakes. However, it's believed that inclusion of new images will make the classifier further improve in this hit rate. So, we have the conclusion and future works, and we can observe that clinical data alone do not archive the best results. Concatenate between clinical data and image descriptor is feasible and produce better results. Not all learning algorithm testing are suitable for classifying renal pathologies we using an hybrid dataset. Resample was fundamental for the good performance obtained by the classifier, but overfitting occurred. So, thank you for your attention. Here my email, and thank you for watching.